The Surgeon General has asked me to give you the following warning. There are no labs in this video. I know, boring. I'll try to make it less boring, I promise. But there's some very important theory covered in this video that's going to affect some of what you see in the rest of this section, and we need to know this stuff. So I want to show you this on the board, and you'll see why in the next few minutes. Now, a BGP speaker, it's going to advertise a route to an internal neighbor under certain circumstances, not all circumstances. Now, if that route was created by the router that's going to do the advertising via the network command, no problem. If the route was learned via static route redistribution or IGP route redistribution, or if the advertised route is a directly connected route, then a BGP speaker will advertise it to an internal neighbor. Now, you look at that list and you say, sounds like a pretty comprehensive list to me, but there's one very common circumstance missing from that list. When a BGP router learns about a route from one internal neighbor, that same router cannot advertise the route to another internal neighbor. And that's a pretty common circumstance. And I put that theory to the test here for you by putting routers 1, 2, and 5 in BGP AS125. And router 5 is advertising 5550/24. And we verify that with show IP BGP 5550 on router 1. And there it is. No problem whatsoever. We see valid internal best. Everything's just fine. But check out the phrase not advertised to any peer. Well, if we go over to router 2 and we run show IP BGP for that network, we see the network's not in the table. So even though routers 1 and 2 are internal neighbors and the adjacency is fine, router 1 learns about a route from an internal neighbor, router 5, and will not advertise it to another internal neighbor, that being router 2. Now, this looks like a pretty darn restrictive rule, because in theory, this would mean that we would need a full mesh in every AS in order for our routes to be propagated properly and punctually. Now, in real-world networking, that would be an unbelievable amount of overhead. And actually, in larger labs, you had 8, 9, 10 routers, and you start trying to build a full mesh, it's just a nightmare. And I'm not saying that because I'm lazy or something, and I'm not saying it about you because you're lazy. It's just asking for trouble. Because the larger that full mesh gets, the larger the chance of a misconfiguration, or you just miss a link, and then all of a sudden you're doing a lot of unnecessary troubleshooting. Now, BGP does give us a way around that logical nightmare, and we're going to see that solution in action very shortly. But right now, while we're at this, I want to show you BGP's role of synchronization. This doesn't come into play a lot. And as you'll notice, it says here on the board, this rule only comes into play when an AS is a transit area and if there are non-BGP speakers in the transit area. So you're not going to see a ton of that, but you might see something like what we see on the board here. Now, AS200 is a transit area between AS100 and 500. And note that the only BGP neighbor relationship in AS200 is between 2 and 4. You can't assume just because you see physical connections that logical connections are fully meshed. Now, the problem is AS200 is a classic hub and spoke config where all data is sent from spoke to spoke, whether it be 2 to 4 or 4 to 2, because notice there's no physical connection shown in the diagram between 2 and 4. It's got to go through the hub, any spoke to spoke communication. But if router 3 is not running BGP, it cannot possibly know about the 220.0.0.16 networks that we're trying to propagate via BGP. So router 3 would just drop those packets. Now, without the synchronization rule, router 4 would advertise a path to 220.0.0 over its eBGP connection to router 5. And as you'd expect, packets sent by router 5 to that network are never, ever going to get there. And the BGP rule of synchronization, here it is. A transit AS will not advertise a route until every router in the transit AS has that same route in its IGP routing table. So in this case, R4 would not send an advertisement for 220.0.0/16 to router 5 until router 4 heard an advertisement for that network from R3 via an IGP. And that advertisement, of course, indicates the non-BGP speaking R3 has a route for that network. Now, If this is the first time you've heard the BGP role of synchronization and your head is swimming a little bit, welcome to the club. I don't think anybody totally masters that role the first time they hear it. And it's important though, because the major benefit is that packets that can't reach the desired destination, they're not even going to be sent. Because why send packets if they can't get where they need to go? Now you run into situations like this with BGP in the real world, but not as often as you used to. And I took it out of most of the configs in the book, but BGP Sync is turned off by default in all of our configs so far. And that is the case as of iOS 12.2.8. So anything you're working with in the real world pre that, probably be lab environment routers, you might have to actually enter the command no sync in there. But if BGP synchronization is on, it is safe to turn it off if all the routers in the AS are running BGP, which they probably are, if there's a full mesh in the AS, or if the AS in question is not even a transit AS. And to disable BGP synchronization, just run that no sync command as shown here on the board on router 5. That's all there is to it. The only time you'd ever have to enter that really though today, I can't imagine pre-iOS 12 routers running BGP these days, but in a lab environment you might have some older routers, no shame in that game, but you might have to put no sync in there. Doesn't hurt. Now, one more piece of theory here, it's BGP split horizon and some full mesh deployments. Now, you would expect BGP split horizon to work just a little bit differently than EIGRP split horizon, and by golly, you would be right. BGP split horizon states that a BGP speaker, cannot learn a route from an IBGP peer and then advertise it to another IBGP peer. That sounds familiar, maybe like something we saw earlier in the same video. Well, to work with that rule, again, we would need a logical full mesh among all our internal peers in every BGP AS, which is simply not a practical idea. It's not just impractical, it's just a terrible, awful idea. And the reason you don't see many BGP full meshes is really the same reason you don't see many frame relay full mesh networks. Overhead. And especially with BGP, because any full mesh deployment of BGP, it's going to hammer your router resources. And of course, as a full mesh gets bigger, what happens? The chances of a misconfiguration or a missed configuration become larger and larger and larger. And again, you end up doing a lot of unnecessary troubleshooting. Now, a full mesh is also going to need a ton of TCP connections. And if you want to figure out exactly how many, here's a quick formula for doing it. It's X times X minus 1 divided by 2, with X being the number of routers. And if you had an AS with 20 routers, using that formula, you would need 190 separate TCP connections for a 20 router AS. We don't want to go there. Really, there are 3 fantastic reasons to avoid full mesh IBG deployments, apparently 2 of which I'm going to show you. An unnecessarily large number of TCP connections are needed. We just saw that. These sessions suck up a lot of bandwidth. And boy, creating and maintaining the full mesh, we know, time-intensive, logical landmine, and we end up doing, for the 3rd time, a lot of unnecessary troubleshooting. Thankfully, there's a solution to all of this, and they're called route reflectors. And we are going to configure those, see them in action, and be right back in the lab at the beginning of the next video. I'll see you there.